Go through our last little bit of review about relative age dating versus exact age dating. So this is also known as like stratigraphy is another word for that relative age dating. At the end of this video, you're going to find links to some other support materials, so you may want to look at those other videos. So in class so far, we've learned 5 different laws of relative dating or stratigraphy. So superposition, original horizontality, lateral continuity, cross-cutting, but also fossil correlation. So the first day we learned 4, and then the later in that week we learned the 5th. So if we ever ask for 5, you know where that 5th one comes from. So today we're just going to look at some of these laws that may be a bit more difficult. So the first one I want to talk about today is original horizontality. That's the one that says you have to have a layer before you can do something to it. So all layers are laid down flat because of gravity. We can see that here, here, and on the top of this one. And then something will happen to either lift one side. So here we can see how this stack got tilted to the side. Or it might be like lifted in the center here. Then original horizontality also applies here when we can see that this hilltop got like erased or eroded down, and then this layer then went across the top. And so gravity will make that happen. So original horizontality is that idea that everything's laid down flat and then something else can happen to it, like a fold or a tilt or an erosion event, something like that. And again, reminder that for those erosion events, we did cut some vocabulary for you. We'll leave that for your college classes, so you can have more fun there. Then the other one I wanted to review quickly today is law of lateral continuity. So remember, lateral means sideways, continuity means continuous. So we can see that here in these 2 examples. This one, it's lateral continuity because these layers are continuing till they reach this bedrock edge here. But that also works for a scenario like this. So here we can see there's gray on this side and gray on that side. Rock doesn't just stop and then hop over and start again. It would have been one continuous layer. So we know that this gray layer matches that gray layer and is the exact same age. The same would be said for this tan layer, and this yellow layer barely at the bottom. And then we can see that same type of fill-in happening that we saw up here, happening down here at the bottom. Lateral continuity is always used when you are talking about cross-cutting, and it's the one that kind of disappears in your head. Like you won't realize you're using lateral continuity when you're like, I just know that one cuts through there. Like that valley, this river valley got cut in there and I know it. Well, how do you know? Well, because of lateral continuity. That used to be one piece. So if you're looking for a law and you can't come up with it, look to this disappearing common sense kind of law of lateral continuity. Then the last one we added was fossil correlation. I think the hardest thing about this one is it's not about the rock, it's about the fossil. So we're using our knowledge of biology here to date rocks. And so what we see is like this snail shell matches this snail shell, so we know those are both the same age. This party horn matches that party horn. So notice how the rock background behind those is different on each side. It's not the rock that matters. Maybe these guys landed in muddy sediment and these ones landed in sandy sediment. And so the rock itself may be a little bit different. But the environment they die in is kind of what that is an indication of. That's not as important as the fact that the rocks are the same age because they have the same fossil. So they have to have these 3 things. They have to be widespread, develop and go extinct quickly, and cannot be tied to a type of rock. Now, all the laws are represented here in this quick little video, so see if you can name each of them. Oh, is it going to play back? There we go. So those are the laws that are represented there, and what I'll do is I'll link this video in the comments section as well as in the thumbnails at the end so you can have a chance to do that yourself and figure out which ones are which. So those are some of the laws we talked about. That's some of the stuff we need to know. But then we also talked about exact age dating. So what if there's too much distance? What if we need something more accurate? So we talked about exact age dating as well. So this is measurable, like knowing someone's birth date or their height. And so we talked about the process of radiometric dating. Again, there'll be another link about how this works. And so it uses radioactive isotopes and decay rates to determine exact ages. So the half-life is the amount of time it takes for a radioactive isotope to decay, for half of it to decay. So this is one of those things like a light year where it sounds like one definition, but it really is something different. And so the half-life is an amount of time. So this is kind of our multiplier. So we also use this image talking about how uranium decays into lead. And what I like about this image is it shows how when that rock is formed, it's all the radioactive parent isotope. And over time, that radioactive isotope decays until you're left with nothing but lead. And so each time about half of that atom decays is called that half-life. So that's about 1 billion years for uranium. And so this rock would have taken 1 billion years for that to happen, 2 billion years, 3 billion years. So if we know the half-life of an atom and we know the ratio of parent to daughter isotopes, we can determine the age. So all different elements, radioactive elements, have a different half-life. So the amount of time of half-life is different, but that decay rate or the graph shape, when we made it with the buttons, that will always be the same. So that graph shape is always the same. But we can use different elements to determine different age ranges. Now the thing is you've got to have, most of these are going to be from igneous rock because that radioactive elements are coming up from the core, which gives our core heat, you'll recall. So your igneous rocks are going to be your most common. You have to have both parent and daughter isotopes present as well. If you have all parent isotopes, that rock, was it born yesterday, 2 minutes ago, 100 years ago? You kind of don't know depending on the isotope present, so you've got to have both parent and daughter. Likewise, it can't be all old. You don't know if it's all daughter isotopes. If that happened 10 minutes ago, 10 hours ago, 100 years ago, who knows? So you've got to have a little bit of each. And then the other limitation to radiometric dating is sedimentary rock. It does not work in sedimentary rock because sedimentary rock is made up of bits and chunks of other rocks. So if you tried to radiometric date a sedimentary rock, are you getting the cement material? Are you getting the sediment material? Are you getting one piece of one sediment material and it's made up of several? You don't really know. So sedimentary rock this does not work for. And then again, like I said, there are lots of different elements that we can use depending on the to determine age of rocks. So depending on the different isotopes, so here we can see how there's different isotopes of uranium which will turn into different isotopes of lead. And they have very different half-lives. So when you're talking about what you're using radiometric dating for, these are like different elements or items that you could use. So the most common one is carbon-14 for a human time scale. So you'll find when they're trying to use this method for things like a mummy or some other artifact from human history, they'll use carbon-14 data. Okay, I hope this helps in terms of knowing what the difference is between relative and exact age dating. Have a great day.